Okay, so ever since people started getting hurt and losing blood, right? We've tried to come up with a way to help people that have lost too much blood, right? There was a lot of trial and error at the beginning. We'll talk about that if we ever make that trip to the Mutter Museum. You'll actually be able to see some of this equipment that people used back in the day. But I think it's important for us to understand how successful blood transfusions go, right? We've learned a lot since we first started putting blood from one person into another, and now we understand the theory behind why it worked sometimes and why it didn't. So, blood typing is about how red blood cells are either compatible or incompatible with someone's immune system. So, let me just give you a little bit of background here. Again, I told you I didn't want to get too much into immunity, but your immune system basically works by having a zero tolerance policy. Okay. Your immune system will not tolerate anything that looks foreign to the body. In other words, anything different. Your white blood cells are basically trained, and it's a long process, but they're basically trained to recognize your own body's normal proteins. And everybody has their own individual little carbohydrate shell on their cells, which allows this recognition. So that's called the glycocalyx. So around your cells, you have basically a unique identifier that your own immune system is okay with. If any other cells come into your system, or any other even materials come into your system, a splinter of wood, a germ, or somebody else's tissue, as in a blood transfusion or in a organ transplant, that drives your immune system pretty much bonkers because it's not something that your immune system ever sees, and therefore your immune system, I mean, just it's pretty reflexive, right? Thinks that it should get rid of that tissue. Blood typing is a really good way to understand that process. So, I just want you to understand that blood cells are identified by what antigens they have on the surface. Okay. They also call them agglutinogens. So I would know right at the get-go, make sure, I wish I could, kind of like, jump this out at the screen at you, but antigens are important to distinguish from antibodies. Okay. So I don't know what it is. I guess maybe it's the anti part in the beginning, but antigens are what give cells identity. So they're those surface glycoproteins, mixture of protein and carbohydrate, that are inherently different between blood types. And in humans, there are four different blood types that you can have. Okay, so what I want you to do is pay attention to this first cell here. This is a cell that has the A antigen on it. It looks like these little blue Pac-Man shapes, right? A antigens, remember, they are the ones that give cells identity, okay? So this cell, therefore, identifies as an A blood type, okay? So this would be a type A red blood cell because these little antigens are the shape that we've designated A. All the little golden horseshoes you see going around this one are B antigens, right? So that means that this is type B. Okay, I'll give you one guess what this is. There's A's and there B's, so yeah, you're right. So that's type AB blood. That means both of these glycoproteins are produced and cover the cell surface. And then you have Baldy over here, right? There are no antigens. See, I just did it. Antigens on that cell surface. And what that means is it's type O. Okay, so A has A, B has B, AB has A and B, type O has none. Okay, at least at this point, we haven't talked about the positive negative thing yet. Let's just go with the first letter, the first symbol. Okay, so that's what antigens are. Antigens give cells identity. Antibodies are proteins that are created by the immune system. So your immune system, my immune system, anything that has an immune system, to recognize non-self, in other words, not the person that the immune system belongs to, organisms and or chemicals, like those little antigens we talked about before. So you might be asking yourself, how do my white blood cells tell the difference between what cells to kill and what cells to leave alone? Well, if your white blood cell is used to seeing your particular antigens all the time, they'll leave those cells alone, any cell that has your antigens. If another cell comes in, including blood cells with the wrong blood type, those antigens are considered non-self to your immune system and they will be attacked and destroyed. Okay, so that can be a real big problem if you're putting somebody else's blood in you and your blood type therefore doesn't match. Okay, so antigens on bacteria, fungi, protozoans, other pathogens, or other molecules are considered non-self, as are people with different blood types or tissue types. Okay, so this does not happen right away. I just want to make sure everybody's clear on that. But after that blood, that foreign blood or that foreign tissue or whatever is in the system, antibodies will start to develop to it. So, generally, if you were to get the wrong blood type, you might not react for a couple days, but then things are going to go pretty bad. Okay, so let me just show you how this works. So, type A blood, right? So these are blood types of, you could say, of people, right? A, B, O, and AB. You can see type A has a little, type A antigens on it. B has B antigens. Type O has no antigens, and type AB has A and B antigens. So, what antibodies would type A blood make? Now, keep in mind, antibodies are what stick to and destroy, well, lead to the destruction anyway, of the antigens that they're meant to fit. Okay, so people with type A blood cannot make, therefore, type A antibodies. Because if they did, those type A antibodies would stick to their antigens, right? So, in other words, this one here would stick to these, and that would be really bad. Okay, so people with type A blood cannot make A antibodies. Can they make B antibodies though? Yeah, they can, because these won't actually fit into the antigens. I try to color code these to make it a little bit easier too. Okay. Type B blood cannot make B antibodies. Otherwise, your blood would be attacking itself, right? Your antibodies would be attacking your B antigens. But if A blood were to get into the system, they can make antibodies that will attack A, right? Type O blood doesn't even have antigens on the surface. So it can make type A and B antibodies, right? Because there's nothing here that A and B could actually fit into to cause a problem. Now, the weird thing comes up with type AB blood. AB blood has both antigens, right? So that means type AB people, right? People with type AB blood cannot make either antibody. If they did, those antibodies would bind to their own cells, and obviously that would be a problem. So, what were to happen if you gave, say, like type B blood to a type A person? They could develop B antibodies, and that would be a problem. What if you gave type O blood to a type B person or type A person? They don't have antibodies. So there's really, or sorry, antigens. See, I keep doing that. They don't have antigens. So there's really nothing for the body to react to. This is why a lot of people call type O, a lot of type O people are called universal donors. They can give their blood type to, well, not everybody, but they can give their type to a lot more people than, say, AB people. Okay? So, how this works again is you have, say, type A erythrocyte. If somebody got, say a type B person were to get this type A erythrocyte in their body, they could make antibodies to it since this would be foreign, right? So we're assuming now, just so it's not confusing, let's say assume B type blood, right? We'll assume that the person in question in this example has B type blood, right? They get the wrong blood type in, type A erythrocytes. Okay, those type A erythrocytes are foreign to somebody that possesses B type blood, right? And therefore, the body will eventually make anti-A antibodies to it. These antibodies, this is kind of how they're shaped, and they fit in that little Pac-Man mouth there. They'll fit in here, fit in there, fit in here, fit in there. And what's eventually going to happen is these antibody molecules will stick all of these cells that have the antigens on them, and they'll start to clot. Now, remember what we said about, having, going on the lazy river and making sure your red blood cells slide through your blood vessels really easily? That's not going to happen if everything's stuck together. That's called agglutination. Okay, so agglutination is the sticking together of hemocytes, in this case, erythrocytes, red blood cells, to their complement antibodies, ones that fit into the antigens, causing blood cells to stick together and clump. That's a really bad situation to be in, because if blood cannot flow smoothly through your blood vessels, that means cells are going to be starved of oxygen, right? At least oxygen. And if that happens in your brain, you're going to have a stroke. If that happens in your heart, you could have a heart attack. None of those situations is good, of course. Okay, the last thing we have to talk about here is Rh factor. So in addition to those two proteins, A and B, there's also another factor called the rhesus factor. Okay, um, that means if you have the rhesus protein, the rhesus factor, on your blood cells, so this is completely separate from A or B or O, right? Um, if you have that rhesus factor on your blood, a separate protein, that means you are positive for Rh, the rhesus factor, right? If you do not have that protein or that glycoprotein on the outside of your cells, that means you're Rh negative. Okay, so since you only have a binary choice here, you either have the Rh proteins or you don't, that's why they're designating positive or negative. A, B, and Rh factor are the most important, I guess, to your immune system, right? So that's why we only consider these proteins when we're talking about immune compatibility or blood compatibility between transfusions, right? Are there other proteins in your blood cells? Of course there are, but these seem to be the only, for whatever reason, these seem to be the only ones that really set off an immune response if you get it wrong. Okay, so as you can imagine, if you had the A antigen, right, and you also had the Rh antigen, you'd be A positive, right? If you had no antigens, right, no A or B, that's O, and say you didn't have the Rh antigen either, you'd be O negative. Okay, so I just give you a couple examples. This is a real important one to get right because it will eventually I think increase your understanding of what we're going to talk about with the immune system. And of course, transfusions happen, right? So you want to make sure, you absolutely want to make sure that you get it right. Okay, so there are problems that can come up though, right? Say two people get together and decide to have a child, right? If mom is, we'll say if the female here is a negative blood type, right? Doesn't really matter what it is. We're only talking about Rh at this point. And the male is a positive blood type, that child, the resultant baby, the cute little baby here, right? Could either be, just because of genetic chance, male or female, or male or female. Well, that's true too, but I was looking at the symbols. Positive blood type or negative blood type. Okay. If mom's body is negative, and dad donates his positive and that results in the baby's blood type, so this baby is going to be something positive, right, so maybe A positive or whatever, right? That means usually for the first child, not a problem, but in labor and delivery, as you guys will see in the video at the end of class, it's kind of a bloody process, right? A lot of tissue gets torn. The placenta comes off of the uterus, and I mean there's all kinds of craziness going on there. That means mom's blood could be exposed to dad's blood, right? And if that's the case, mom will build antibodies to dad's positive Rh factor, okay? So, all right, so say this couple stays together and they have another baby, right? And that baby did also again get dad's positive blood type, right? Now, the problem with that is mom has already primed her immune system to not like dad's positive blood. Well, guess what mom and baby share? They share, well, not quite a bloodstream, but they at least exchange material between their bloodstreams. What can happen is mom's antibodies can go into baby and start to destroy baby's blood cells, right? So talk about a crazy combination of events here. Unfortunately, that actually leads to a lot of miscarriages. So, is there a way to fix this? Rh factor can actually be, I'm sorry, the Rh response, the Rh antibodies can actually be blocked by a immune modulator called RhoGAM. RhoGAM is just a protein that pretty much keeps mom's immune system busy, for lack of a better word. I mean, I don't want to really get too deep down into this explanation because it's a little bit tangential. That will pretty much prevent mom's antibodies from attacking baby's blood. Okay, so there is for sure some precedent for this, but there is a way to fix it too. This is why it's extremely important. Anybody out there that's planning on having kids, if mom's already had a baby, and it could be a aborted baby, it could have been a miscarriage or an actual live birth, that can be a problem if the male and female's blood type is incompatible.